You know that feeling when you're staring down a massive spreadsheet of historical data, and it honestly just feels like you're looking at a completely unsolvable mystery? Every little fluctuation, every peak, every valley, it's kind of like a crime scene full of hidden patterns that are just waiting to be cracked. Because time series data, it isn't just some random collection of numbers, it's actually a highly structured blueprint of the past. And the crazy thing is, if we can decode that blueprint, we can literally build a mathematical model of the future. Welcome to The Explainer. I am so excited to be your guide today as we unpack one of the absolute most powerful tools in data science. So, here's the big question we're tackling today. How exactly do we predict the future when our data is just constantly changing? Well, think of us as data detectives. We're going to be hunting for literal fingerprints left behind in historical data, extracting those hidden structures, and then using them to forecast what happens next, and doing it with absolute mathematical confidence. Okay, let's dive right into this. Here is our blueprint for today. First, unlocking time series patterns. Second, the ARIMA model explained. Third, the 5-step Box-Jenkins method. Fourth, solving a real-world example. And finally, generating your final forecast. All right, part 1, unlocking time series patterns. Okay, so before we can solve our mystery, we really need to understand the fundamental nature of the data we're looking at. Time series data is basically just an ordered sequence of values that are measured at equally spaced time intervals, right? So by applying time series analysis, we're extracting meaningful statistics from these points to figure out the underlying forces that actually produce them. And since these points are collected over time, they have this built-in internal structure. We're looking for things like trends, those gradual shifts to higher or lower values over a really long period. We're also hunting for seasonal variations. Those are the predictable, repeating sequences of highs and lows within a set time frame, like over a year or even a single month. And, absolutely crucial here, we are tracking autocorrelation, which is essentially how a single data point relates to its own past values. Moving right along to part 2, the ARIMA model explained. So once we get that our data has this hidden internal structure, we need the right mathematical tool to actually capture it. Enter our master key, ARIMA. It stands for AutoRegressive Integrated Moving Average. It's a highly sophisticated forecasting model that uses correlational techniques to model time series behavior. The real game changer here is that ARIMA is specifically designed to accommodate complex patterns, like when you have combinations of trends and seasonality, by stabilizing the variance in the data before it ever even attempts to spit out a forecast. Now, what's really interesting about this slide is how the very DNA of this model breaks down. ARIMA is defined by 3 specific parameters, P, D, and Q. So P is the autoregressive, or AR, part of the model. D stands for the order of differencing, which are basically the steps we take to stabilize our data. And Q represents the moving average, or the MA part of the model. Whenever we sit down to solve a time series mystery, our primary goal, literally the whole point, is to discover the exact numerical values for P, D, and Q. Which brings us to section 3, the 5-step Box-Jenkins method. To actually find those P, D, and Q parameters, we use a super systematic approach called the Box-Jenkins method. You can think of this as our ultimate architect's blueprint. There are 5 relentless steps we absolutely must follow. Step 1, make the data stationary. That means giving it a constant mean and variance, usually through that differencing technique we just talked about. Step 2, identify the specific P and Q model parameters using correlation plots. Step 3, fit the likely models to the data and check if they're statistically significant. Step 4, verify the model by checking the leftovers or the residuals. And only then, step 5, generate confident future forecasts. I cannot stress this enough. We have to progress through every single step. Skipping even one totally compromises the whole investigation. Now, step 2 is where the real detective work kicks in, and we use these visual cheat sheets, the autocorrelation function, or ACF plot, and the partial autocorrelation function, or PACF plot. Think of these as our visual guidelines. An AR process, that's the P in our model, is indicated if the ACF decays exponentially, while the PACF just cuts off abruptly after a certain lag. On the flip side, an MA process, the Q, is indicated if the ACF cuts off sharply, while the PACF declines exponentially. And fun fact, for most real-world data, you honestly won't need more than 2 AR or 2 MA parameters. All right, section 4, solving a real-world example. Okay, Enough theory, let's actually apply this blueprint to a real-world case. We are going to solve the mystery of forecasting employment levels in the food industry. So our raw data here showed a really clear repeating seasonal pattern every 12 periods. The autocorrelations just weren't dying out. Because of this, our very first Box-Jenkins step required us to make the data stationary. To strip out that 12-period seasonality and force a constant mean, we applied differencing, specifically taking a seasonal difference of 12. This leaves us with a brand new set of stationary data, which we're going to call food diff. So let's examine the clues left behind in our new stationary food diff data. Looking at the ACF plot right here, remember our cheat sheet from a minute ago. We're looking for significant spikes that cross those red boundary lines. The way these spikes behave, whether they just chop off abruptly or slowly decay over time, is the visual evidence that helps us zero in on the necessary moving average, or Q, parameters for our model. Next up, we flip over to the PACF plot for that exact same food diff data. Here, we're scanning for the AutoRegressive, or P fingerprints. Once again, we're looking closely at the significant spikes at those initial lags to see if they cut off or decay. By comparing the behavior across both of these plots side by side, we can basically narrow down our list of suspects to find the absolute perfect mathematical fit. And this brilliantly illustrates the whole elegance of the Box-Jenkins method. By systematically analyzing the spikes in both the ACF and PACF plots of our difference data, we successfully track down our parameters. Based on those exact visual patterns, we decided to test an ARIMA model with an autoregressive order of 1, a difference of 0 on the non-seasonal part since, remember, we already handled the seasonality earlier, and a moving average order of 1. So we're looking at an ARIMA 101 model. Finally, part 5, generating your final forecast. All right, we've identified our prime suspect model. Now we enter the final phases of the investigation, fitting the model, verifying it, and getting those predictions. We feed our selected ARIMA 101 model, along with that seasonal difference of 12 from step 1, into our statistical software. Check out the t-values and p-values for our parameters here. Our AR1 coefficient has a highly significant p-value of 0.000. Our MA1 coefficient has a p-value of 0.440. We rigorously examine these statistical significances just to guarantee that the model we picked genuinely provides the best overall mathematical fit for all that historical data. But wait, hold on. Before we start popping the champagne and generating our forecast, a good detective always double-checks their work, right? This is Box-Jenkins step 4, verify the model. We actually have to check the ACF and PACF plots of our model's residuals. The residuals are just the errors, the leftovers after the model does its thing. We need these leftovers to look like pure, completely random noise, which means absolutely no large spikes remain on those plots. If there are still large spikes, well, that means our model missed a hidden pattern, and we got to go back to the drawing board. But if the residuals are pure random noise, we are officially cleared for step 5, generating our confident future forecasts. So think about what we just did. We took a seemingly chaotic, massive sequence of numbers, broke it all down by trend and seasonality, identified its unique mathematical fingerprints, and built a structural model to actually predict its future. Time series analysis isn't magic, it is architecture. It's building a framework. So I'll leave you with this. Knowing what you know now about the Box-Jenkins method, how might you apply this structured ARIMA blueprint to extract hidden patterns and predict the future in your own industry's data? The clues are out there, you know? You just have to look for them. Thanks so much for joining me on this explainer, and I will catch you next time.